neurotransmitters. So that's what we're going to talk about right now. With neurotransmitters, first let's make sure that you remember the definition of a neurotransmitter. Of course, it's a type of chemical messenger, but it has to meet two criteria. It has to be released from a neuron, right? And it has to be released very close to the receptor. So if it's released from a neuron and gets picked up by the bloodstream, it's not a neurotransmitter, it's a hormone or a neurohormone, but definitely not a neurotransmitter. So it has to meet both of these criteria. Neurotransmitters are the language of the nervous system. It's how neurons speak to one another within the CNS, brain and spinal cord, and in the PNS as the nervous system talks to other tissues and effectors. So we'll talk about lots of CNS neurotransmitters, and we've already talked about some PNS neurotransmitters because we've already talked about the somatic nervous system and how it uses acetylcholine, for instance, to control skeletal muscle, and the autonomic nervous system and how the autonomic nervous system uses both acetylcholine and norepinephrine to control the autonomic effector organs. Okay, so there are at least 60 neurotransmitters that have been identified. We're not going to learn 60 because we don't know what all 60 of those do. We are going to learn a small subset that you're going to run into in clinical settings or just being a human. More are being found all the time. Most of them are relatively small, by which I mean they're low molecular weight, not huge. Here, for instance, is acetylcholine. When I show you the chemical drawings of the molecules, you're never responsible for them. It's just so that you can get an idea of how big they are and how some things are shaped like other things, that kind of stuff. So most of them are relatively small, meaning that they're low molecular weight. And because they're small, low molecular weight, they tend to diffuse relatively quickly across the synapse, which makes them fast acting. And what they do is they bind to receptors on the postsynaptic cell. And they can either start an EPSP, excitatory postsynaptic potential, or they can start an IPSP, inhibitory postsynaptic potential. And that really depends on whether they cause a depolarizing graded potential on the postsynaptic cell or a hyperpolarizing graded potential on the postsynaptic cell. So, often for a single neurotransmitter, there's more than one receptor subtype. And really how the target cell responds has more to do with the receptor on the target cell than it does the neurotransmitter. So a neurotransmitter could be excitatory in one place and inhibitory in another place. I'll try to avoid saying, for instance, that acetylcholine is an excitatory neurotransmitter. And instead, I'll try to keep myself saying acetylcholine is a neurotransmitter that usually binds to excitatory receptors, although I will probably make a mistake from time to time. Since it's more about the receptor than the neurotransmitter, the response to a single receptor or a single neurotransmitter tends to be tissue specific. So it has to do with what types of receptors that tissue has for the neurotransmitter. Okay, so before we get into the specific neurotransmitters, I want to talk a little bit about how neurotransmitters and the drugs associated with them and the receptors associated with them are named. So unfortunately, there's not a single consistent naming convention because sometimes, often actually, an exogenous chemical was found before the neurotransmitter was found. So for instance, although a lot of you guys haven't heard of a chemical that we're going to learn called anandamide, you have heard of cannabis because cannabis has been used for hundreds of thousands of years before we knew anything about neurotransmitters or receptors. So how are these named? They're named cannabinoids because we knew about cannabis first. The ones that are inside of us are endocannabinoids, and the ones that come from elsewhere are exogenous cannabinoids. So often the impact of the drug is known long before we know about the neurotransmitter or the receptor in the body. So if that's the case, then you're going to find things named like opioids that are named for the opium poppy. So People used opium, for instance, for thousands of years before we discovered opioid receptors and endogenous opioids like endorphins. But conceptually, the receptor and the chemical messenger had to predate the drug, or else no one would have ever used the drug. So what I'm saying is you don't have opium receptors, and don't let anybody tell you that you do. You have receptors in your brain, for instance, that bind to a naturally occurring endogenous chemical and also bind to opium. Okay? So, how are the neurotransmitters and the receptors named then? Two kind of naming conventions that are pretty common. Where did it go? Sorry, I lost it. So the drug, like an opium derivative, can give rise to the receptor name, like opioid receptors. We call them opioid receptors. Or you found the chemical first, the endogenous chemical first, and then named the drug after it. So GABA is a neurotransmitter, gamma-aminobutyric acid. And we named the receptors GABAergic, and then we talk about the drugs as being GABAergic drugs, but that's because we found GABA first. Okay? All right, so we'll stop right there, and then I'm going to get into the chemical classes of neurotransmitters.